So we are back again live. Next Coda stream. We'll continue from where we have left off. Uh, let's minimize OBS. The title is Coda Stream 2. Let's add a hashtag. Save. Okay, so we are live with Coda Stream. I have this chat GPT. This is where we ended last. YouTube music. Let's close it. Okay. Now I have opened two windows only. So this is where we did end last time. So the fun thing is I did something very sort of silly, you can say. My GPU got crashed. The story is actually pretty interesting. So the story is like uh, I ran like 1 million threads of this kernel and my GPU crashed, because of which my streaming stopped. Why my streaming stopped? Because my OBS was using my GPU to encode the video data. NVIDIA uh, SMI NVIDIA SMI. I guess this is the command. Yeah, see this one. This thing. This is my OBS process that's consuming my GPU to encode the video live. I didn't know about this, that my OBS was using the GPU in my system to do the live encoding of my video to stream. So when I ran 1 million threads in my GPU, maybe the memory consumption went much above that, and that process presided over this one, and maybe because this process got killed, something like that happened. You can actually watch NVIDIA SMI so that this stat get refreshed every time. Yeah, it is not found. Okay, okay, sorry. I typed in the command wrong. It is NVIDIA SMI, not SMI. Yeah. Now this stats gets refreshed every 2 seconds. So it's like sort of live. I got a refresh rate of 2 seconds. Exit this. Okay. And got done with the housekeeping. Let's start where we have ended up. Where we have ended up is actually this one. So I started giving these two kernel parameters. One is the grid size and another is the block size. My block size contains the number of threads inside each block, and grid size is basically number of blocks inside a grid. I don't know what parameter this is, but when I give this parameter, there is no issue. Okay, uh, there is something called CUDA cuboid. Uh, CUDA cuboid. CUDA grid, uh, grid and block. And block. There is this nice. This is what I was talking about. A group of threads is called a cuda block, and cuda blocks are grouped into a grid. This is the one thing um, Dylan Patel in Lex latest podcast was talking about essence, a streaming multiprocessor. Each CUDA block is executed by one SMs. Okay. So if I have got n blocks and each block containing m number of threads, so I require m SMs to execute my m blocks parallelly. No, actually one SM can run several concurrent CUDA blocks depending on the resources needed by CUDA blocks. Each kernel is executed on one device and CUDA supports running multiple kernels. So this is the diagram. Like have a CUDA thread. Say block contains multiple CUDA threads and a grid contains multiple blocks. Each block is executed by one CUDA SM. Okay, so I guess so this grid contains multiple blocks. Each block is executed by one SM. Something like this, I guess. This is the official NVIDIA documentation. CUDA defines built-in 3D variables for thread and blocks. Threads are indexed using the built-in 3D variable thread index. Three-dimensional indexing provides a natural way to index element in vector, matrices, and volume. So volume is like matrices stacked upon one another and giving it another dimension to matrix, which are inherently 2D. CUDA architecture limits the number of threads per block. Okay, really, really. Let me check this one. If I give more than 1024 threads per block, what will happen? Uh, I remove this kernel parameter. I have only one block and I run 100 threads. I guess it will print something. So let me compile the file. NVCC file name is t.cuda. Let the name of the executable be t and I execute dot slash t, I guess. So my 100 threads running. So I guess I can start NVIDIA. It will be fun to watch this at the same time. NVIDIA SM. I get a little bigger. No, that's fine. Okay, that is a power spike. So 9 watt to 10 watt. No, I think this spike is happening anyway. There is no limit to the number of threads that can be contained in a given block. So I'm like, this is not an issue right now. You see this parameter, it is the thread number. Now this will work or not? No, this didn't work. This did not work at all. Wow, such a beauty. Hmm. So this is actually true. So it didn't get executed because I have exceeded the limit of number of threads in a given block. Now this parameter, what you can see here exactly, contains number of threads that can be executed in a single block. It is set to 1024. I make it 1025. So it doesn't execute. I make it 1024. It executes. So let's take note. Let's take note while we are learning what all we learn. Um, uh, the number of threads. Uh, let's write be more specific. Cuda threads that can be contained in a block at maximum is 2 power 10, I guess. It's 10 to the power 20. So this is one thing we discovered right now. The dimension of the thread block is accessible. Okay, there is something called block dimension variable. All threads within a block can be synchronized. Okay, what does that mean? Synchronizing the number of threads in a block. All threads in a block must wait before one can proceed. All threads in a block must wait before one can proceed. Before anyone can proceed. Threads per block, blocks per grid are these kernel parameters. Type int or dim3. Okay, so dim3 is a data type in CUDA. So that's why if I write dim3, I get some syntax highlighting, I guess. Okay, so it's a custom data type in CUDA. If I write dim3, it gets highlighted. I can also write int. So what these triple angle brackets do, they mark a call from host code to the device code, and this is called a kernel launch. So this specific statement is actually called a kernel launch. Uh, this is called this is called a kernel launch. The CUDA program for adding two matrices below matrices. What that is called, I don't know. The CUDA program for adding two matrices below source, multi-dimensional block IDX and thread IDX and other variables like block dict. So this is a matmul. We'll get into it later. It's not that straightforward. Let's try to get a hold of the basics of this CUDA architecture. SM is streaming multiprocessor, I guess. SM we got. What that was? It is called this multiprocessor. If I saw it. Yeah, it is streaming multiprocessor. Hmm. So This piece talks about the memory hierarchy and this about compute capability. So what's this PTX? Parallel thread execution instruction. I get it's the instruction set architecture for the CUDA architecture. Like CUDA is basically architecture only, but like it's like assembly for GPUs, NVIDIA GPUs. This is the instruction set architecture for the NVIDIA GPUs. Parallel thread execution instruction (PTX). Okay. So for our GPU is 3050 RTX 3050. Um, I guess I get a version number. I don't know what's the version number of my, like this is the version of the driver like 535.183, where is 535 and 183 is Y. Y is the minor revision number and X is the major revision number. Mhm. Okay, because some part of the code runs on uh, CPU and some part of the code runs on GPU. So it runs in a heterogeneous environment. एहसास तेरा हो गाही नहीं दिल चाहता है मुझे कहने दो इसे. Both host and device maintain their own separate address spaces or formally memory spaces. The host code and the device code maintains their own separate address space, and there is a bridge which is responsible for the data transfer within the host and device memory. So there is host memory, and then I have got this device memory. So like the CUDA programming models allows distinct management of these two separate address spaces. I can call it address space. In more technical language, compute capability. So let's talk about the memory hierarchy. The registers that private to each thread, which means, so if I assign a given register to a given thread, that register is not visible to other threads. So a register is private to each thread. No, here is not a node. Here is a node. A register is private to a thread. If one thread is using a register, it is not visible to another CUDA thread. Okay. Then there is L1 memory, L1 level cache. This is the level on cache. Shared memory. Every streaming multiprocessor has a fast on-chip scratchpad memory. This is the phrase on-chip scratchpad memory. What's this? On-chip, on-chip SRAM. Acha, this is called scratchpad memory. I got to learn a new term. The scratchpad memory. This is the data memory residing on chip that is mapped to an address space, disjoint from the off-chip memory. Okay, this is a bit technical, this description. What it says, data memory residing on chip but is mapped into an address space, disjoint from off-chip memory, but connected to the same address and data buses. I can't comprehend it. I think this is more comprehensible. A small high-speed static RAM located directly on the processor chip. It's like the concept of cache. Like this is more closer to the actual unit which does the computation than the VRAM. Like in context of CUDA, we are using a GPU. So it's like RAM is VRAM and this what this is called scratch pad memory. Like L1 cache is being called scratch pad memory here. I guess in CPU also you call that it. It is essentially dedicated scratch pad for the CPU to quickly write and read from it. Okay. The name Scratchpad also makes intuitive sense in the sense that whenever you get some idea, you just jot it down. You just like quick loading and offloading data. That's why the name Scratchpad comes from, I think. Uh, so every SM has an on-chip memory. Normally, the idea of a thread is also used in a process. If there are n number of threads, all those n number of threads share the resources allocated to that process. The same concept also sits in here. All threads in a CUDA block. So you can think of CUDA block as a process, analogous to a process in a CPU or OS, like in a software abstraction. They consume the same resources allocated to the not consume. Share is more appropriate here. They share the same resources associated to the, I guess, process. Mm, every SM has an instruction cache, constant memory, texture memory, RO cache. So many new terms here. Okay, L1 is like every SM has got a L1. Now L2 is like all the SMs share a L2 cache. And this is the VRAM, what you are saying, the frame buffer size. Like there's like L2, L1, there is like VRAM. Like L1 is like every SM has their separate L1, which you can call a scratch pad. And L2 is like multiple SMs share a L2 space. That's the memory hierarchy. I got this cube. Yeah, this one I like this CUDA cube. Yeah, this thing. Like you can think of the CUDA programming model on three axes. One is grid, block, thread. Mhm. This is one. I think this makes sense. Mhm. So the outermost wrap is grid. Inside that you get block, and inside block you get multiple threads. So what is this extra parameter then? What is X, Y, and G? I want to understand what's G. Thread IDX dot G. I want to understand this. Now, X and Y is more or less clear, I guess. Like if I have two blocks and like three threads in each block, and I print this stuff. Like the first one is X, second one is Y, Now y will be 0 and 1, I guess. Or two. Yeah. No, it doesn't make sense. Like 0, 1, 2, this is the thread index. Like these are the three threads running in the one block. These are three threads running in another block. But this thread idx dot y parameter it's same for both, which means it doesn't indicate different blocks. What it is? Okay, no idea. Maybe we figure it out with time. Let's get to some interesting images. Maybe I'll get a better hold of it later, I guess. Okay, the thing either I can pass this, nah, or I can thread dim, which is let's say 3, dim 3, dim block. So there is this data type. Then instead of 2 and 3, I can actually give two data types in the parameter of this kernel. Either it is an integer or I pass it this dim3 data type, which is a block dim, comma, the thread dim. I guess this will be fine. Ah, this is fine. Or I can also pass integer too. If I rename the data type as int, I don't think there will be any problem. Execute it out. No, there is no problem. So in CUDA, there is this custom type called dim3. This actually looks good. Let's use this. This makes our code look different than C++ or C. Let's use this one for time being. Uh, okay, let's do something. I have the live memory uses here. Let me declare some variables and then offload those uh, variables to the GPU memory and see the memory usage here going up. We can see the memory usage here going up. If I create a bunch of variables in my host memory and then uh, transfer it to the device memory, that would be a thing we can try out. Okay. Um, छूने से तेरे आ तेरे. Let's give it a more detailed one. Just be precise and crisp, um, and answer what I ask. Do not say unnecessary things. Hmm. Defining variables in post and transferring it uh, to CUDA. Like there is this function called memcpy, memcopy. Uh, I have heard of it probably. The generated code will use that function. We'll see. This is like the fundamental of GPU. You do memory management, you do memory allocation. Let's define a variable in our CPU right now. Uh, okay, it will be fun. Like it's int, which is post variable, post view, and it's four letters. It's an integer. Yeah. Now I do something. Uh, it does some complex operation. Like it uses cuda malloc. It first allocates some memory in the GPU. How it allocates? Okay, I get a pointer variable referencing to that memory location, and it's just like you do it in C. You define the type of it. Okay, it seems like a more sophisticated allocation. Do a less sophisticated one for the time being. Yeah, this is a more simpler approach. It seemed like it has squeezed in a lot of efficiency there, which I do not want to understand right now because I'm just getting introduced into this thing. This makes more sense. You declare a pointer variable and then you use this function cuda malloc managed. So you allocate the size of int, which is 4 bytes, to this pointer, and you can dereference this pointer. This lets both CPU and GPU access var without manual data transfer. But the question is where the var is stored. Where the var is stored in VRAM or RAM. Acha. So it abstracts away the migration of the data. When I use this CUDA malloc managed, so it abstracts away the process of transferring data from the CPU memory to the GPU memory. So we don't need to think about that. The CUDA drivers handles the migration, but it is stored in the GPU memory, not in the what you call that, not in this CPU memory. It the function is CUDA malloc managed. Really a nice function. Okay, uh, uh, let's allocate some space. Mhm. So let's create some pointer variable. Mm, It's a pointer variable. Let's print the pointer. I have forgotten what's the uh, address specifier of a pointer in C. Address specifier of a pointer in C. It is percentage %p. Okay, percentage %p, comma, I write ptr. Uh, this is CUDA memory alloc manual. So how you do the malloc? Okay, it's uh, actively managed thing. It takes two things. One is the I guess it will take the memory address of var. Why it takes percentage ampersand var? It is already a memory location now. I don't understand it. Let's go by the rule as of now. We'll do that later. And I allocate some memory. Let's say size of int times let's say 1000. I look at short memory. So int is 4 bytes. Uh, I look at a thousand of such 4 bytes, which is 4,000 bytes, which is like 1,000 bytes is roughly 1 megabyte, like 1 kilobyte. Let's see the memory usage. We'll do the calculation later. I just want to see the memory usage right now. Let's don't do kernel launch and device synchronization here. We'll do that later. I just need to see this thing. Let's dereference it and print something. No, like I do size out. We'll do that later. We need to see the spike in memory. What is the memory usage right now? 359 megabytes, and I guess it would be more than that right now. No, no, I really need to like this. This is declared but never referenced or used. Let's comment this out. I have this variable reference. This cuda malloc managed. I have to like declare some more numbers unless it is not visible. I guess it's so kilobytes, megabytes. So like from bytes to megabytes, it's 10 power 3, I guess. No, like 1,000 bytes is 1 kilobyte, and 1,000 kilobytes is 1 megabyte. So it is 10 power 6. Yeah, it's in the order of 10 power 6 to go from kilobyte from bytes to megabyte. So it's mega. That's it. 10 power 6 is mega. I guess I need enough number of. So you go from raw bytes now. Okay, you don't go from bits to bytes. You go from bytes to megabytes. So it could be 6 zeros. Like right now, I have 3, 4, 5, 6. I guess it would be right now 4 megabytes. It should go to like like 363 MIB right now, more or less. Let's check that out. Clear the terminal. Let it refresh. There is no spike in memory usage. Why the warning is coming? Acha. Let's print the address, memory address. I guess this should not be an issue. And I guess I need to run a loop to just keep the memory allocated off. Else, I guess once the program stops running, this like makes the memory free. That is like free. That's why it is not showing anything. I just don't do anything. I don't do anything. What I do is I need to do some fake computation, I guess. Like f10 is equal to I assign this multiple times. Now just to see the memory usage going up here. There is no other purpose of this. Yeah, now I can see. Yeah, exactly. That was the thing. My CUDA driver was freeing up the memory once my program was stopped executing. Once the program like gets finished, my CUDA driver frees up the memory. So the spike in the memory usage is there only for a moment, and I can't notice it in that moment. So what I need to do is I did this. My process, like there is this process going on in the GPU, consumes 68 megabytes of memory. Okay, got it. E was declared but never referenced. Can I run an empty while loop, by the way? Is this possible? I don't know. I've never tried. I think it should be possible. Yeah, it is possible. the memory usage spikes. And if I halt the program, it drops. Suddenly, all the memory allocated to this process becomes free, and I can see the drop in the memory usage here. Actually, very nice. Now, this thing is managed by CUDA malloc managed. Let's note down the function I discovered. Like this will be very handy. CUDA malloc managed. Like it's like more abstracted away. I don't need to manually move the data from the CPU memory to the GPU memory. The data is by default stored in the GPU memory, but my CPU can also access it. This transition is managed automatically by the CUDA driver. So it's like more abstraction. It's a function which lies at a much higher layer of abstraction than MEMCPY, I guess. We'll check this function like right now. There is a function something like this. So as far as I remember, like I saw it somewhere. This is CUDA malloc managed. I don't know. This is a pointer variable. Huh? Okay, got it. Like it will store the memory address. So it is 2 bytes. So if I dereference that memory location, uh, got it. It's not like type check. Okay, I guess it got something interesting. Okay, 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 okay. Why didn't the memory location get printed? It should have got printed, I guess. But that did not happen. Why? This thing is not happening. Why? Maybe it is not allocated right now. If I go right, maybe right now this will work. Uh, Alt, function down. No. Why? No idea. If I attach another zero, it's like hundreds of megabytes get used in this process. Yeah. No, it's only 68 MB. How? I have allocated more memory, man. How it is 68 MB? Stop the execution. I should not crash the system, I guess. No, it's again 68 MB. Something interesting is going on. Okay, okay. If I allocate only 1 byte, 4 bytes, what is the memory usage I want to see? It's 68 MB. So my hypothesis was wrong. It's not the allocated memory, I guess. It's something else. Like my GPU usage is obviously going on, but it's not about the variable like allocation I'm doing. Then why it is only 68 MB? It should change like depending on, is it not getting multiplied? I'm not using not using parentheses. Uh, how is it constant always? 68 MB. I don't understand this. Okay, we'll try it later. Check out some other function. Oh fuck! It's lazy execution. This is unified memory. Okay, that's the beauty of it. This is something called unified memory. Um, memory. This does lazy allocation. That means the memory is allocated just before you try to use it. Okay. So, fuck man, NVIDIA has done such like intricate optimizations. Immediately allocate physical memory to GPU. Instead, memory is allocated in the system's RAM and pages are migrated to the GPU VRAM only when accessed by the GPU. Okay. If you haven't accessed the allocated memory from a CUDA kernel, it remains in the system RAM, that means the host RAM, and doesn't show up in the GPU memory usage. Try launching a kernel that reads or writes to WAR. You should see the GPU memory usage increase. Okay. Hmm. Just give me a list of functions. Make a list of common functions used in CUDA for playing around with memory, just like CUDA memory, CUDA malloc managed. It's auto managed malloc managed. So now we have got a list of CUDA memory functions to play around with. Like I think we need to be very clear with the mechanisms of this function at a like input output level of abstractions to like I should like get a hang of these functions. It's a double pointer. So this CUDA free, it frees up GPU memory. It doesn't free up automatically. It doesn't even allocate. Previously, I was thinking that CUDA malloc managed was automatically uh, freeing up the memory when the process ends. But the reality is, it is not even allocating the memory first to the GPU variable. It was just keeping it in the system RAM. So it is similar to lazy loading into the VRAM. They only use the memory of the VRAM and only offload it to the GPU memory only before I require it. So it makes like very efficient. Clear out this function. Nice. Let's play around the functions. We have been streaming for the last 50 minutes. I guess you have got a better context of CUDA. So this is for free. This is managed unified memory. It first allocates the memory in the CPU, and whenever I require the allocated memory for a process for a kernel in GPU, it loads the like the data into the GPU memory. This is unified memory. Like the data transfer is abstracted away by the CUDA driver. You don't need to think about bringing the data from GPU and taking it into the GPU. It is managed by auto manage. That's why it is malloc managed. You don't manually manage the malloc, it's auto managed. This is host alloc. Allocates pinned page logged host memory. The beautiful phrase I heard of it is page logged host memory. We'll get into that. What it actually is. This mem copy async. This is asynchronous memory copy. This is memset. I guess like the memset function is also there. It sets a value to allocated memory. It's also in like C++ memset. I don't know whether it is there in C or not. I never used it. Must be there, I guess. Let's search it up. Edge memset uh, there in C. Yeah, it's there in C. So it's just prefixed to its, the string cuda. So it's cuda memset. It's camel case. Fine. Function names are camel case. Class names are Pascal case. That's the standard mostly. Sets GPU memory to a specific value. First, I need to allocate the memory. Then I need to um, then I need to set the value in that memory. So to allocate the memory, I use this cuda malloc. What it takes? It takes the pointer and the size. Now that's what it did in the beginning, I guess. It used cuda malloc. It took a pointer and a size. Why it uses this double pointer? Let's check the error method. If I get a use a single pointer, it must decay to a double pointer, something like that. Like it's querying the memory, CUDA pointer get attributes, CUDA mem perfect async, prefetches managed memory to a specific device. So they're like some sort of more advanced function. I don't think we need to play around it right now. I think I need to get the hang of these two functions in the beginning. That is mem CUDA malloc, CUDA free, and CUDA mem copy, mem cpy. Let's start with CUDA malloc and CUDA free and see the memory usage spike here in the NVIDIA SMI. So let's say let's like just comment all these things out. This CUDA malloc. What's this double pointer? I need to check. Describing. So it is not unified memory. Directly allocates the memory on the GPU VRAM. It takes two parameters, a pointer to the pointer that will store the allocated device memory address. Okay, it's a bit beautiful. Why it takes a double pointer? You need to understand it. The malloc, when I used in C, it takes a single pointer. But when I use CUDA malloc, it takes a double pointer. Why? A pointer to the pointer that will store the allocated device memory address. Okay, when I use it, I get a memory address. Okay, wrapping my head around this is not going to be straightforward. What is size underscore stc? To have this lightweight queries, let's open Gemini. Uh, size underscore team. What is that? It's unsigned integer. Okay. It's defined in standard def.h. So it's size underscore p unsigned integer. A function updates this to point to the allocated memory in RAM. Okay, first of all, it is a pointer variable. When you define a pointer variable, the idea is you can always dereference it to extract the value. Or else, I can simply declare an unsigned integer to store the memory location. But I cannot dereference it to extract the value in that memory location. So that is the difference between uh, declaring a pointer variable and a normal unsigned integer variable. In a normal unsigned integer variable, although I can store the memory location, but I cannot dereference that to extract the value in that memory location. But if I declare a pointer variable, I can always dereference it to extract the value inside it, and the value inside it is assumed to be the type of the type of pointer I'm using. So if it is int star p, when I dereference the value in the p memory address, it is assumed to be of an int type. So if the type of the pointer is void, when I dereference it, it can get typecasted into anything. Okay, that was a little bit of a distraction out here. So it's a double pointer. So it's basically a single pointer. You decade that into a double pointer. It's complex. So you have used ampersand this. This is the okay. It's complex. Like there are two. It is complex. Simplify. Pointer to the pointer that will store the allocated device memory address. Pointer to the pointer to now this is a nicer explanation. Think of cuda malloc like this. You have a pointer. So this is a pointer I have d underscore arr. Now that should point to a GPU memory, right? Now this needs the address of this pointer to modify it. This function needs the address of this pointer to modify it. Understand this. I require the memory address where the pointer variable is stored. Now the pointer variable is 2 bytes. I require the memory address of this pointer variable where the 2 bytes is stored. So cuda malloc requires that address. Cuda malloc requires the address where the pointer variable is stored so that what it can do. Why it requires this? Imagine you want to write your friend's phone number on a piece of paper. Okay. You want to write your friend's phone number on a piece of paper. If you just give me the number, I cannot change it. Imagine you want me to write your friend's phone number on a paper. This is the memory address of this. Imagine you want to write your friend's phone number on a piece of paper. If you just give me the number, I cannot change it. But if you give me the paper itself, I can write the number on it. DR is just an empty pointer at first, finds a space on the GPU and writes the address to that space into DRR. Okay. The DRR points to a GPU memory. You can use it in CUDA kernel. Okay. That's fine. But like why cannot CUDA malloc simply store the memory address getting me to the internal source. This is the core of language design. Passing a pointer to DRR. I need to do some experimentation around it to get a hang of it. This is not easy. This is not easy. It might be easy, but it's a lot confusing. Okay, let's just do what it says and see the memory usage. I have a pointer in my memory. It's post like post post PTR. Like this is not like how you have a host pointer and I use how I use it. I first dissolve the pointer into a double pointer. And then I allocate the size of the range and go to that one shot. It will be like 1 MB right now. That will be the case. I guess that's okay. Take the memory usage, it's 359 MB. I'll execute the program. Yeah, now I can see the spike in memory usage. Actually, it is 72. If I let make it to 3, it should improve. If it is improving, Um, it increases, if you can see. It increases to 80 MB. It is not constant like before. But, but if I stop running this, okay, that's actually nice. Where is the empty while loop? There is no empty while loop, no? Uh, what's the warning? The warning variable is used before its value is set. Acha, I don't want the variable to be set. Okay, let's run this. Okay, I have not used the infinite while loop, but still the program is not stopping. Wow. Can I see what this return and print it out? I guess I can't print things like this here. It doesn't work like. No, no, actually. I can just see the spike in memory usage. If I use 30, I get 30 bytes. Yeah, it started using 184 megabytes. Like 1 megabyte is 1024 kbytes. So, like it's 2 power. It comes in the order of the power of 2, not power of 10. So that's the difference between megabyte uh, and megabyte. So megabyte can be 1000 kilobytes or 1024 kilobytes, but 1 megabyte is always 1024 kilobytes. So it is like brings in more specificity, more what do you call that? Clearer, like make the things more clearer, more defined, more standardized with this. Okay, you know what is the issue? I get this might be this. Now I guess I need to run a while loop. While on RL, I cannot see the memory usage. Yeah, it's 184 MB allocated to this process because I have allocated this many bytes, this many 4 bytes into because I've allocated this many 4 bytes, so I can see my memory spike here. Some issue like this is the memory address. Why don't you simply print it out? Printf will work. Why it won't work? To see thing na. I'm definitely not doing something correct. That's why it is not working. Percentage P comma. I guess I didn't mention ampersand. It means the memory address. No host PTR, no. Host PTR. No, it is not printing. This printf function is not working. Doesn't PTR like ask it? Doesn't printf function inside the main thread doesn't work in a cuda program? Yes. Acha. Printf inside the main thread works normally in a CUDA program. However, printf inside a CUDA kernel requires special handling. Host code it will say, but why I'm not able to print anything if it works fine? For me, it's actually different. That is some network error. Printf works normally in host code. Works. Acha, it is how it is getting executed, but like at the layer of syntax, it is same. But there is an issue. This is not getting printed. Like, can I print anything else? Hey, I this piece of memory, I guess. Yeah, but previously it was getting printed. This was getting printed. How how this was getting printed? If I let's say like do this thing, it will get printed. I think there won't be any issue for getting this printed. No. Why? But if I do this, all this starts working perfectly fine. I need to understand this. What is the issue? In this setting, these printfs are working fine. These printfs are working fine. If I'm running the code like this, but so once I allocate memory, I don't know what is the issue, and it doesn't stop the execution. Like I think it should print test func the number of times, and it should execute. There is some issue. I need to figure out. It doesn't stop executing. Why? Ah, why it didn't stop executing? Acha, it is stuck in this while one loop. That's why it is not getting executed, but fine. Like it is fine. But if I comment these two things out, I run that program where I declare a pointer variable and I need to print the pointer variable, and then I need to get the return value of CUDA malloc, which is 0 if successful, 1 if not successful. Then I print R. Uh, I don't need these two things. Then I may start execution, printf. I run this. I guess there will be some issue. This is happening. Okay, was this the one causing the issue? Empty while one. If so, why? Why a empty while loop might be causing the issue? No, now the issue is not there. I don't understand it at all. Okay, uh, let's start with this thing. There's a new line. I decided new line. You don't just start execution. I need to print this memory address in CPU in host. Let's try to use the terminology, the right terminology, the standard terminology. host for my CPU memory, and the device for my GPU memory. Memory address in host. Let's print it like this, and there's a new line. Okay, so this is the host memory address. It is in hexadecimal. Okay, how many bytes are getting allocated? Okay, now we have got the like it is working. I don't need to experiment with this. Let's just reduce the memory usage. Right, I don't need to allocate 100, but just allocate 1 4 byte, and that 4 byte also has got a memory location allocated. Now, while the return statement is not getting printed, it must print something. Before I was like it was printing zero, or at least maybe I was interpreting this zero as the return zero. It might be the case. How unstructured my thinking is. This is the host pointer. This is the memory location. This is a variable which will store a memory location. Now, what if I pass this? I want to understand. What if I pass this? There is an error. It takes a pointer to a pointer. Okay. What if I print without memory address? Let's keep this thing consistent. But hmm, memory address in host. It's an unsigned integer, I guess. So we can print you. Will not get this one. I get the value. Uh, Before its value is set, I get some value. But if I see P, I see a hexadecimal output. Yeah. So I guess it stores some random wrap values there. Okay, so I have this pointer variable. I need to make the memory address, so some garbage value gets stored. Um, the host PTR is a pointer variable of integer type. I pass the this one I need to understand. I'm not able to get a hang of this thing. I'm not able to get a hang of this thing. So the memory address is this. You address it to the malloc, and now you print p. Let's say I print post ptr. It must have changed. Post underscore ptr. It stores a memory address, and that memory address should be two different addresses. Yes, this is got it. I guess I got it. This is memory address. Memory address in device. Ah, I guess I need to do this. Like, what is it doing? See, this is the memory location inside my GPU, and this is the memory location inside my CPU, the virtual memory address. This is of course virtualized, but yeah. So, if I keep a value here, how should I keep it? You have to understand things well. Now, this memory location, this memory location holds this memory location, which is the location inside GPU, which holds the actual value. Now, if I can play around with GPU memory right now, if I let host pointer 20 and I print percentage d plus n host underscore it's not print, it's printed. That's the side effect of writing Python so much. Okay, let's clear this. Let's print this out. Now I will see everything. And why you have done this? You just need the value. You need to dereference it, not give it the memory location. Why is the code done? It's a pointer variable. I dereference it, I store the value. And if I print it, again do segmentation for now. Like, how can I? This is not in the payload, I guess. This address is not in CPU. That's why I'm not able to dereference it. Maybe that is the case. Because if I create some another pointer, let's say int star p, and I store the value star p is equal to 5, 4, and before that I print the value. This is like control C, control V. Instead of post pointer, I write p and dereference it. I don't think there will be an issue. Wait. So many things happened. So I have two pointer variables. I dereference it, add the value 4. Okay. And then what I do, let's do this thing. Ah, although I'm getting the warning, I'm able to dereference it. See, I'm able to see dereference it. That's the beauty. If for the value is set, this diag subscripts. Warning, but I'm able to dereference it. But, why I'm able to dereference it? Because the memory location is in my in my host, not in my device. But this memory location, the host pointer, I assign the value 90. But the value when I dereference it, I cannot because the memory location is not of my host, not of my CPU. It is the memory location of the GPU. So I can't dereference it, I guess. Yeah, that's why I'm getting a segmentation for it. Hmm. We'll check that out. If I takes a double pointer, I get enough of stream for today. Let's meet in the next stream. Bye, guys. Bye. We have streamed for like 1.5 hours almost.